Hello, so let's kick off some questions on material. So things to do with Young's modulus and stress and strain and things like that. Start off with a graph of stress against strain for rubber. Use figure 8.1 to describe the main physical properties of the material. Okay, so we've got number one, it is elastic. And how do we know that it is elastic? It's because the strain returns to zero when the stress is removed, which is a nice way of thinking of something being elastic, as in, so the stress is the pressure that we're putting on the material. This is the force that we're applying here, because that's force over area. The strain is the extension over the length, so that is what's happening to the material when the stress is applied. So if we got something which is elastic, it's going to go back to how it was at the beginning, as in when we remove the force, the extension disappears. So that's one thing. We've got that it is non-Hookean, so it doesn't obey Hooke's law, because we don't have a straight line, so not a straight line graph. So we can tell that. Then we've got, I suppose we could also say that there is work done on the rubber during each stretch contraction cycle. Stretch contract cycle. And we can see that in this, it's the gap between the loading and the unloading curve. I think the area under the curve here, this is the work done, because we've got a force times a distance going on in this area under the curve, but we're not getting that work back, or not all of it, when we unload. So we have to put more work in to stretch it than we actually get back when it releases. So another way of putting that is that the load and unload curves are different. So that covers pretty much everything, at least what I can think of at the moment, for what that graph is telling us. Figure 8.2 shows a metal strip pulled from its ends until it breaks. So they've given us the dimensions of the strip, which is that, and that, so we don't need that bit in the question. They've given us the breaking force and the Young's modulus. Calculate the extension of the metal strip when it breaks. State one assumption made in your calculation. Okay, so we've got that Young's modulus is equal to FL over AX. We want the extension. So that is giving us that the extension is FL over A times the Young's modulus. So our extension is going to be F is 16, L is 15 centimeters. So we'll change that over to 0.15. Actually, let's keep it all in. No, I will do that. I was wondering if I'd just make that into a 10 to the minus 2, but we'll leave it as it is. Right, because I will be doing that probably in all of this. So we've got the area, we got 1.2 times 10 to the minus 2 multiplied by, I'm going to say 1.8 times 10 to, so we'd have minus 3, 4, 5, 10 to the minus 5. Then we've got Young's modulus, which is 7.1 times 10 to the 10. Okay, so we can deal with some of these tens going on here. So we've got minus 7 off of there, which makes that a 3. And now we just got to type everything in and see what we end up getting. 1.6 times 1.5 on the top, and then divide by 1.2, divide by 1.8, divide by 7.1, which gives us 0.156. We're at two significant figures, so I'll put that first of all 1.56. I'll just make it a bit smaller, so that'll be 10 to the minus 4. I mean, move it along a decimal place and put a 10 to the minus 1 in. So that is going to be 1.6 times 10 to the minus 4 meters, and that is to two significant figures. State one assumption made in your calculation. Well, there's a number we could go for here. I mean, we've assumed that this is Hookean, so we could put that in. We could put there's no plastic deformation. I mean, it's much the same thing. Any of those sort of ones that we come across with these materials. Calculate the breaking force of a rod of radius 0.6 centimeters made from the same material. Right, well, in this, if you've got the same material, this breaking force is, or the breaking stress is going to be the same. So that's why we're doing this stress calculation. So the breaking stress will be the same. Breaking stress is the same. So our force over area is going to be the same for both of them. So we've got that 16 divided by these units, the 1.2 times 1.8 times 10 to the minus 7. That is going to be equal to whatever we're looking for divided by our pi r squared. So that is pi multiplied by, what was it, 0.6 squared, 0.6 squared, and then we're going to have a 10 to the minus 4 in that, times 10 to the minus 4. So let's deal with all of this then. So we get rid of that, make that a 3. So our F, I'm running out of space, so I'm just going to start typing this all in. We're going to have 16 times pi multiplied by 0.36, and then we got to divide by 1.2. We got to divide by 1.8, and then we've got our 10 to the 3 to put onto that. So that's 8.37, give or take, 8.37 times 10 to the 3. So 8.4 times 10 to the 3 newtons, again to two significant figures. So yeah, that's an interesting addition, that one, because sometimes we get so fixated on Young's modulus that we just look at, oh well, that's going to be the same for a material, although that's not necessarily going to be the case. There are subtleties to Young's modulus depending on what direction you're pulling materials and things like that, but they're going here for this idea that our breaking stress is going to be the same for this material, regardless of what its its dimensions are, and that's something that we're working with, at least at this stage. Again, we're making more assumptions there. Things do vary. If you've got fibrous materials, it depends what direction you're pulling them in and things like that. So we can't just apply this willy-nilly and say, oh yeah, this is fact for all material, but that certainly seems to be what they're getting at here. Otherwise we don't really have enough to work out what's going on. Right, now we've got a spring question. We've got a spring of unextended length 2 centimeters hung from a fixed point. We've got a weight of 3 newtons. They've given us that in the picture, hung from the other end. Figure 7.1 shows the length of the spring when the object's in equilibrium. Okay, so it starts at 2 centimeters. We've now got an extension here of 6 centimeters. Later on, we're going to have an extension here of 10 centimeters whenever we decide to pull the weight down, by the look of it. Show that the force constant of the spring is 50 newtons per meter. So the force constant, K, that is our constant of proportionality in Hooke's law. That's our F divided by X. So that is 3 newtons divided by a 6 centimeter extension, 6 times 10 to the minus 2. So that's a half times 100, 50 newtons per meter. So that's a nice starter. Object is pulled down vertically. Yeah, we've now got an extension of 10 centimeters. Calculate the change in the EPE. Right, so elastic potential energy is the average force multiplied by the distance. So that's average force times extension. So that is a half kx average force multiplied by extension, half kx squared. That's how we get that EPE formula. So our change in EPE is going to be our final EPE minus our equilibrium, EPE. So that is a half multiplied by 50 multiplied by 10 centimeters squared. So I'm going to say that is 100 times 10 to the minus 4. So I've put in 10 to the minus 2 and then squared it, just to make the numbers a little bit easier. I don't want to have these huge, hugely small decimals floating around. And then we got half times 50 times, so 6 centimeters squared would be 36 times 10 to the minus 4. So that is going to be 25 times 10 to the minus 4 times 100 minus 36, which is 64. Well, 25 is 100 over 4. So that will leave us with 16 times 10 to the minus 2. Which is 0.16 joules. So it's nice they gave us some nice numbers there to keep us away from the calculator. Object is released from its position. Calculate the initial upward acceleration A of the object. Right, so we're into now Newton's second law, F equals ma. So our net force on this is, don't forget the weight. We've got the force in the spring is going to be K times X, which is 50 times 0.1, but we've got weight acting in the opposite direction, which is 3, and that is going to be equal to the mass, which is 3 divided by g, the weight divided by acceleration due to gravity, and then multiplied by the acceleration. So we got 5 minus 3, so that's 2, so the acceleration is going to be 2g over 3, which is going to be just short of 2/3 of 10. So 2 times 9.81 divided by 3, 6.54. So let's say 6.5 meters per second squared, just keeping it to two significant figures. Right, we're back on the graphs again. We got figure 6.1 shows the stress against strain graphs for two materials. Describe the properties of materials X and Y. Right, so we usually want to say about 4 things with all of this and combined. So for X, we can say that it is brittle, as in it just extends up to the snapping point. There's no deformation or anything, no stretchy bit that happens before it breaks. So it's brittle. We can say that it is Hookean. It obeys Hooke's law because we've got a straight line. We can say it is elastic because it returns to the origin. You know, the strain goes back to 0 when the stress is removed. So we can say all of those about X. What can we say about Y? We can say that it is non-Hookean because it's not a straight line. We can say also that it is elastic. So we've got the same thing going on there because it's returning back to the origin. So this is going to be, you know, rubber, something like that. I mean, you might even want to say that in there. But we've said quite a few things already. Right, now for B. You're given a spring, a meter rule, and a 100-gram mass. Describe how you determine the force constant of the spring. Right, so you want to, first of all, measure length of spring. Yeah, without the load. So without load, without the mass. Then add the mass and measure length again. Measure length again. Then we can say that the force constant is going to be equal to 0.1 multiplied by g, that's the force, divided by the extension. And you might want to just add in that the extension is the difference in the lengths. And then that will give us whatever it gives us. Right, so now a glider of mass 0.18 kilograms placed on a horizontal frictionless air track. One end of the glider is attached to a compressible spring, a force constant 50 newtons per meter. The glider is pushed against the fixed support, so the spring compresses by that amount. Calculate the horizontal acceleration of the glider immediately after release. So it's going to be whatever the force is going to be. So we're going to do F equals ma on this. We're going to do Newton's second law. The force that we're going to have is going to be the spring constant multiplied by 0.07. That is going to be equal to 0.18 multiplied by A. So we just need to stick all of that into the calculator. 50 multiplied by 0.07 divided by 0.18 gives 19.4. So the acceleration is 19.4, which equals, yeah, we're still on two significant figures. Oh, we got 3 on one of them, but not enough on the others. So I'm going to stay on 19 meters per second squared. Yeah, they sort of tempted me in a little bit with this mass here, but we've still got just a straight 50 on the force constant, so I don't want to get carried away with accuracy. After release, the spring exerts a force on the glider for a time of 0.094 seconds. Calculate the average rate of work done by the spring on the glider. Right, so this is going to be the energy, that's going to be our EPE divided by the time, because the EPE in the spring is going to the glider. That's what's happening to it. So we're going to have a half of kx squared, 0.07 squared. I've already done my half of k, so that's k is 50. I was writing in 25 because I was thinking about half of k. So half of 50 multiplied by 0.07 squared divided by 0.094. So 25 times 0.07 squared is that divided by 0.94 gives us 1.3 watts as a rate of work done, because we've got energy per second going on here. So 1.3 watts. Yeah, quite a nice question.